So good morning, everyone. Today I will talk about this detailed electro-optical modeling of TADF OLEDs with different host gas concentration. So just to summarize what I will talk about, first I will describe our experimental and modeling approach that we used. I will briefly describe the OLED stack that we received from a collaboration with Augsburg. And then I will discuss the three main results and that we found then with this study. So regarding the experiments which we performed, we used PHOTOVOLTAICS, the instrument that you might have seen in the exhibition outside. And in this study, we performed the steady-state transient and impedance measurements. So we measured the JVL curve, injection sleeve at different voltage offset, and then capacitance versus voltage at different frequency, and the other way around. So capacitance frequency at different voltage. Regarding the modeling, we used the Sept. So with Sept, we can define our OLED, our stack, and then we can simulate the experiments which were performed with PHOTOVOLTAICS. So basically what we used in this case is the combination between the two, which is called Sept-PHOTOVOLTAICS integration, SPI. And basically we can first we define the OLED stack with Sept, and then by comparing the simulations of the experimental results and the experimental results, then we can find a good agreement between them. So basically the idea is that it's an iterative process. So we start from an initial set of parameters from literature, for instance, and then by repeating the simulations and comparing with the experiments, we can find the set of parameters which best describe the experimental results. And here another point to mention is that it's really important when we are talking about OLED to take into account several experimental techniques. Because basically with Sept we model the stack, yes, but we have several layers. And also we have, every layer depends on many parameters like mobility of electrons, holes, energy levels, excitonics in the EML. So the idea is that when you take into account many experimental techniques, then you can reduce the correlation between the parameters. And then at the end, you can really trust your results. So here is the stack that we received from Augsburg. So we have all transport layer, TCTA. Then the EML, which is MCV-PCN and DMAC-TRZ, which is the TADF emitter that we have already seen yesterday in a couple of talks. Then we have a very thin layer of DPAPO, which is used as an exciton blocking layer, and then TPBI as an electron transport layer. In this case, I already indicated TPBI with minus and plus, left and right, because we have already seen yesterday that TPBI is especially polar. And we defined the TPBI in Sept as a polar layer. And then, so we studied for concentration for devices. So with a percentage of DMAC-TRZ from 5, 10, 20, and 50%. So here are already the result of the simulation. So here we are in the last step of the optimization. I will not go through all the details, all the comparison between experiment and simulations, but just we can note that here, for example, in the experiments, we already see quite a strong difference between the 5% and the other concentration. And we can see that it can be represented in simulations. And also maybe we can have a look at the injection sleeve, where with only 2 volts as an offset voltage, we see just like a small broad peak here, while with 4.5% we see really strong peak initially, and then also at the end the same kind of broad peak. And we see that also in the simulations. Well, it's not really perfect, the shape, but the general idea and the mechanism is the same. Yeah, so just a detail, just to be clear. So in all these simulations, for all the devices, we use the identical parameters for all the layers, TCTA, DPAPO, and TPBI. Is just for the EML that we change parameters like mobility, energy levels, and so on. Now let's discuss about the 3 main results. So first of all is charge transport. We identified 2 regimes. Basically, the low concentration regime, which we used in the 5% in the simulations of the 5% device, where we assume that we have transport on the host molecule, and then the act molecule in this case act as a trap state. And so we define it in Sept in this way. So we use the HOMO-LUMO level of the MCV-PCN, which is the host, and then we define the trap states to mimic the presence of the guest. And then there is the high concentration regime, which we used in the 10, 20, and 50% concentration, where we say, okay, we have an effective HOMO and LUMO levels, which lie in between the levels of the host and the guest. And then, of course, these depend on which percentage we are simulating. So in the 10% concentration, the HOMO-LUMO will be more similar to the host, while in 50% it will be more similar to the guest. And here is again, the same experimental results and simulations of the JV that I showed before. So we see that there is a nice agreement, and we see that also in simulation we replicate the quite strong difference between the 5% and all the others. The second point is the polarity. So we notice that for a 50% concentration, we have a small shift of the transition voltage. And so in this case, we notice like a difference between different concentrations. So when you dope with 50% concentration or with 5%, you see a change of the polarity of the EML. And this was included only in the 50% concentration. And then as a third point, we tried to estimate also some excitonic, especially the annihilation processes. And we did that by fitting the luminance efficiency roll-off, so a different current. And so we tried to estimate the triplet annihilation, TTA, triplet polar quenching from the electrons and from the holes. And here is the result. So we see that by increasing the concentration, we see an increase of all these rates. Here you can notice that. So this is the scaling of the TPQ from the holes, and we see now they look more or less similar to the other two, but actually this scale is 2 orders of magnitude less than this one. Just to be clear. But of course we know that it's not easy, it's very difficult actually to be able to estimate these parameters from a simple JVL curve, because they will be also correlated. It's super difficult to be able to distinguish between TTA and TPQ just from the roll-off. And here in fact we evaluated also the correlation metrics of this fit, and we can see that the correlation between the triplet polar quenching from electrons and TTA is super large, it's 0.92. So from this fact, I would say that yes, we can find numbers for these two processes, but I would be careful by arguing that these numbers are super correct and we can easily distinguish between the two. Another interesting point from these metrics is that instead the triplet polar quenching from the holes and the other two parameters, the correlation is pretty small in this case, at least compared to the other one. We see 0.6 and 0.41, which is not really high. And so we went in detail and we tried to understand why this happens. And so here we did some simulations where we simulated only the 10% device, and we evaluated the loss of triplets at different currents. So basically it's the same. So we have current here, and we evaluated the loss of triplets. So here you see the pink part is super large, and here in this plot it's indicated as a loss. But actually it's not a loss, because here is a TADF, so it's a loss of triplets, but they become singlets. So at the end we have emission from these triplets. The real three processes which gives loss are the TTA and TPQ from electrons and holes. And here we can understand why TTA and TPQ from electrons are highly correlated. Basically both of them, so the yellow and the red part, they have a super strong influence at high current densities. And that's why you cannot distinguish between them, and they are highly correlated. Instead, what we saw is that the triplet polar quenching from the holes is especially important at low current regimes. And again, this is related to polarity. So because basically what we saw also yesterday is that when you have a polar layer, you have an early injection of holes and accumulations. And this means that already at low current densities, there is quite a strong presence of holes inside the EML. And that's why you have more annihilation processes from TPQ from the holes at low current densities. So the conclusions. So we saw that we can identify these two transport regimes with the 5% and the other concentration, identifying these low and high concentration regimes. We found a change in polarity somehow during with different concentration. We said that with low concentration we don't have a strong polarity of the EML, but then when we increase the concentration, the polarity also increases. And then we were also able to understand the effect of TPQ from electrons, holes, low current density, high current densities, and correlation, and so on. So I would like to thank my colleague from Fluxim and also from the guys from Augsburg for the collaboration, and also you all for the attention.